Okay, good morning. My name is Kai Yang from Penn State. First, I would like to thank the organizers for the opportunity to give this talk. So it's about preconditioners for the time discretized system of FSI. It's a collaborative work with my advisor, Professor Jinchao Xu at Penn State, and it's supported by funding from DOE and NSF. Here's the outline of this talk. First, a brief introduction of FSI, and then the final element discretization. Based on the discretization, we introduce some preconditioners, and at the end, some numerical examples. So just some applications of FSI. First is in the cardiovascular system. It's the interaction of the blood with the heart wall and the blood vessel wall, so that we will have blood flow in our vein. And the second type of application is in the hydroelectric power generator. It's the interaction of water with the hydroturbine. So the hydroturbine will be rotating and also have some deformation. So it's necessary to do some simulation to study the frequency of the vibration in order to reduce the damage to the turbine. Here's a movie we made in our group to show you some ideas of this interaction. Although the deformation may not be so easy to be observed. Okay, next we talk about some mathematical model of FSI. So for fluid structure interaction, the interaction is on the interface. Due to the interaction, the location of the interface is time dependent. Therefore, the domain that the fluid and the structure occupies will change. Here, the notation is that with the subscript F, we refer to fluid. So it's the fluid domain and the structure domain. With the head, it is the reference configuration, and without the head is the current configuration. Some notations, we use U to denote the structure displacement, and V to denote the velocities. P is the pressure, and some notation for stress. The function space we introduce is for fluid velocity and the structure velocity, and they will be continuous on the interface. This is very important. This V is for the velocity of both fluid and structure, and then the space Q is for the fluid pressure. Here we have the weak formulation of FSI. The first equation is a momentum equation. It has both the fluid part and the structure part involved. And the second equation is a continuity equation. It's only about the fluid. And here is the very important continuity of velocity on the interface. Another information for this model is that the interface will follow the structure displacement. Therefore, the location, this gamma is the interface. The interface will follow the structure trajectory. So this is also a kind of an unknown in this model. The difficulty for simulating FSI, there are two main items. The first one is the difference in coordinates. Fluid is in the Eulerian coordinate and structure is in the Lagrangian coordinate. The second one is the moving interface. Since the interface is moving, for the fluid, we know that we already discretized in the Eulerian coordinate. Since the domain is changing, we have to adjust the mesh so that it will fit this moving domain. There are several discretization approaches for the moving interface. The first one is the arbitrary Lagrangian Eulerian method. So it will locally move the fluid mesh so that it will accommodate the structure motion on the interface. This is what we use in our study. And there's another type of approaches is the fixed mesh approach. So for this approach, the fluid mesh does not need to move. The first one is the immersed boundary or fictitious domain method. So for this method, it is assumed that there is a fictitious fluid in the structure domain, and for both fluid and the structure, they have fixed mesh, and the interaction is achieved by doing some interpolation between two non-matching mesh. And the second one is the phase field and level set method. So some indicator function is used to determine which domain is for fluid, which domain is for structure. Some more about the ARE method, since it is what we consider in our study. For ARE method, we are looking for a diffeomorphism from the reference configuration to the current configuration. This omega f is a changing, is time dependent. So it has to satisfy this boundary conditions, but in the interior it is arbitrary as long as it is diffeomorphism. In order to uniquely determine this mapping, usually we let it solve some partial differential equation in the interior, for example, the Poisson equation. With the ARE, we have to change the discretization of the derivative in order to avoid the interpolation. We introduce this time derivative with respect to this A, and correspondingly, we have to change the convection term. There's an additional term since we changed this time derivative. Okay, then it's about the solver issue, how to efficiently solve this FSI problem. The first one is the easiest to develop since it is based on a fluid solver and a structure solver. But there are some instabilities. For example, this added mass effect and is unconditionally unstable for certain parameters. Although some remedies has been proposed recently to reduce this instability. For the implicit method, there is semi-implicit and the fully implicit method, so that they will be more stable. Our solver study is for this two implicit methods, so that hopefully we can improve the solver and it can be solved efficiently. So our work, the solver we will present will couple the fluid and the structure equations. Note that the mesh motion will not be included in the linear system. So it can be used in both semi-implicit and fully implicit method. First, we do the time discretization, do implicit discretization like backward Euler. And here we introduce the structure velocity, so that in this linear system we have fluid velocity, structure velocity, and fluid pressure as the unknowns. Note that here for this discretization we do not include the nonlinearity from the convection, so we discretize the convection term explicitly, so that we can carry out some theoretical study. I want to mention that in the practical commutation, we do some Newton linearization for this convection term, so that the system we get is no longer symmetric. Here, this system is symmetric, and we will introduce the saddle point formulation for this system. First, define the bilinear form A and B. We can write the linear system in this saddle point formulation. And also, we define the norms carefully. Here, we add this additional div term, and this parameter, there's a parameter R is the maximum of a list of parameters. We can prove that as long as the finite element pair is stable for Stokes equations, then this formulation for fluid structure interaction is uniformly well posed with respect to all those parameters. That shows the sketch of the proof. We just try to verify the Brazy conditions. So most of them are quite straightforward to show. And for the inf-sub condition of B, we can start from the inf-sub condition of the Stokes pair, of the stable Stokes pair, and do a harmonic extension to prove that it holds for the FSI problem. So we have showed that we have provided a stable formulation. On this page, there are two additional formulations with some stabilization term added. Here we add this R times this div, and the second one we add this R times this div term, and here's the projection operator to the pressure space, and we change the norm for velocity space accordingly. And for these two formulations, we can also prove that it is uniformly well-posed, as long as we use the Stokes stable pair. So based on the stable formulation, we want to propose some robust preconditioners. This procedure is kind of standard here. We just refer to this mapping property. The mapping property says that given a well-posed formulation or well-posed variational problem, then the risk operator will be a optimal preconditioner. It can be easily shown that the preconditioned this condition number of the preconditioned system is uniformly bounded. So since we have showed that the well-posedness for the formulations are uniform with respect to the parameters, then we can follow this procedure to find the block preconditioners that are uniformly optimal for the problems. Okay, in this table we showed the preconditioning strategies. First, some notations. We use this matrix notation A, B, D, and MP to denote the discretization of the corresponding bilinear forms. Okay, for this table, in the second column, it is the discretization of the system matrices. So this is the finite element discretization of the FSI problem. In the first column, these are the preconditioners we developed. The first stable formulation is this M2. Note that here we do not need any stabilization term in the discretization. And for the two additional stabilized formulation, we need to add some stabilization term in the discretization so that actually the problem is changed. Although the preconditioners for M1 through M3 are quite similar, they are all in a block diagonal fashion. And this SC is the approximate short complement preconditioner, is what we use for comparison. This is the approximate short complement. This AHD is the diagonal of AH. This approach is applied for other problems in the literature, like the mixed formulation of Poisson equation, and also some Navier-Stokes equations. There are lots of references about this type of approach. Here we just applied it to FSI. Okay, here's a little brief summary about the preconditioning strategy we considered. Originally, we have to precondition a coupled system for fluid and the structure. By developing those block preconditioners, we just need to precondition the velocity block, which is SPD systems with discontinuous coefficients and a large derivative term. This is the term we added in the norm. It may be quite large. And for the pressure, it is mass matrix is easy to precondition. Okay, at the end, some numerical examples. Here we use this benchmark problem. It's a 2D problem. We have 3 different meshes. They have more and more degree of freedoms. We use this P2, P0. They are stable Stokes pairs. We compare this performance with the approximate short complement preconditioners. The iterative method we use is mean res. We use these preconditioners to precondition this mean res. Stopping criteria is 10 to the power minus 8. And here for each diagonal block, they are solved exactly. And in practice, we definitely have to use some multigrid. But here to show the theoretical result, we just solve them directly. On this page, I showed the number of iterations for preconditioned mean res. There are some varying parameters since our theoretical results shows that these preconditioners should be robust. The first one is the K. K is the time step size. We take 3 different time step size in the first table, and we have 3 different problems. They have larger and larger. Their size goes larger and larger. For this M1 through M3, these are the number of iterations for the preconditioner we proposed. This SC short complement is what we use for comparison. And similarly, in the second table, we change the density ratio of the fluid density and the structure density. And we also use 3 different meshes. It can be observed that this M1 through M3 are quite robust for this varying problem size and parameters, where this approximate short complement will depend on those parameters. Okay, the velocity block, in the numerical example, the velocity block is solved directly. And for some practical concerns, we definitely have to consider what kind of multigrid will be robust to invert the velocity block. So this problem is like this. It has larger jumps in the coefficients alpha, beta, and gamma, because for fluid and structure, they will definitely have quite different properties. And also, we have a quite large derivative term for the fluid in the fluid domain, because due to the it is in the norm we introduced. So here's the question: how to design solvers that are robust for these difficulties? I was very glad to hear that on Wednesday that the discontinuous coefficients should not be a problem for multigrid. That is very good news. And also for this large derivative term, some possible solutions are multigrid methods with special smoothers and use some kernel-aware discretization, such that the functions in the kernel of this derivative term can be represented by a combination of bases, so that multigrid can be designed more efficiently. There are lots of future work about this FSI problem. First is about how to design multigrid for this velocity block, and also when there are asymmetric terms from the convection, how to change the preconditioner accordingly. And also, we're also considering this part, because sometimes it's better to use the power elastic material model to characterize the human tissue. So the fluid power elastic interaction, we will also consider this one in the future. So this is all of my talk. Thank you for your attention.